Hello, my name is Zach, and I'm a part of Team 3, along with June, Matthew, Connor, Jared, and Allison. We plan to analyze and redesign the mounted manual pencil sharpener. The function of this device is to sharpen wooden pencils of various sizes. The user turns a crank to rotate helical cutting gears around the end of a pencil to make a sharpened point. The case of the pencil sharpener catches the shavings, protects the user from the sharp helical gears, and reduces the noise of the sharpener. The wheel on the front of the case can be turned to accommodate different diameter pencils. The primary customer group for this product is school administrators and office managers who would want a rugged pencil sharpener that can be permanently installed. The secondary customer group is individual customers who may want it to be more portable. The expected production volume for this product is about 100,000 units annually.
This is the exploded view of the mounted pencil sharpener kit. The pencil sharpener has three sub-assemblies, including shaving catcher, sharpener mechanism, and crank sub-assembly. On the right side, you can see the detail of the shaving catcher sub-assembly with size selector. The left side is the crank sub-assembly that takes mechanical energy from the user and transfers it to the sharpener sub-assembly shown on the right side of it. The sharpener mechanism consists of multiple gears that accepts the user input and cuts material from the pencil inserted at the center.
Here is our fast diagram for the pencil sharpener. Our primary function is sharpen pencil, and that breaks off into our two sub-functions, which are cut wood and control movement. We accomplish the cutting of the wood by transmitting mechanical energy and accepting manual input from the user. We control movement by aligning the pencil in the sharpener and also securing the unit to a flat surface, such as a table or a wall. We assure dependability by preventing injury during the cutting operation. We assure convenience by containing the shavings for later disposal. We enhance the product by accommodating sizes of different pencils, and we please the senses by minimizing noise during the cutting operation. Here is the function component mapping matrix for the pencil sharpener. As you can see, there are some components which only accomplish one function, and some functions which are only accomplished by one component. This lack of overlap is unfavorable for manufacturing and assembly, as it reveals inefficiencies in the design, which need to be eliminated.
Our primary user group is office workers and administrators in a professional setting. Our secondary user group is private citizens who would use the pencil sharpener for personal use. The majority of the functions are common to both groups. How the unit is secured to the surface is different from each customer group. The primary users want a permanent fixture for long-term reliability and to prevent theft, whereas the secondary users prioritize the ability to move the sharpener and not cause damage to their walls or furniture. Thus, the only module that changes for varying user groups is the base. For the primary user, the base permits permanent fixture to a surface with two screw holes. For the secondary users, there will be two options for temporary fixation. These options are a suction cup or a clamp. These components would be added onto the bottom of the base using the common interface. The existing two screw holes can be used to attach the suction cup or clamp. This means that the base can be the same for all product variants, with differentiation delayed to the last step in assembly. This is illustrated here in our assembly sequence diagram.
Based on the assembly sequence, we have modified three features for better manufacturability. On this table, we can find that it is estimated to take 165.72 seconds to assemble the product with the original design. However, with the three modifications, it is estimated to take 142.7 seconds, which is 23.02 seconds faster and resulted improvement of assembly efficiency by 0.03. As you can see, the three modifications are including combining bearing shaft and gear mount, combining base and sun gear, and gear mount redesign for easier alignment.
We chose to focus on the shavings catcher as the sub-assembly for the design for automated assembly analysis. We performed 3 redesigns to assist in decreasing the total handling and insertion costs associated with automated assembly. The first redesign is integrating the case middle into the case front and case back by making them injection molded parts. This follows DFAS1 by minimizing the total part count. The second redesign is combining the size selector lock and the case front into a single part. This also follows DFAS1, minimizing total part count, and DFJ1, eliminating fasteners, since there was a rivet dedicated to holding the size selector lock on the original design. The third redesign is removing the snap fit, attaching the case front and the case middle, and using an adhesive to attach the two parts instead. This follows DFJ3, since snap fits are undesirable for automated assembly. The tables shown here show the automated assembly analysis before and after the redesigns for automated assembly. The redesigns resulted in a 67% reduction in the total assembly cost of the shavings catcher, which was originally 34 cents per assembly and is now 11 cents per assembly.
Shown here are the 6 key dimensions of the pencil sharpener base. Number 1 is the center-to-center distance of the screw mounting holes. Number 2 is the diameter of each of those holes. Number 3 is the overall width of the part. Number 4 is the sun gear pitch diameter. Number 5 is the bearing shaft hole diameter. And number 6 is the overall height of the part. Presented here are the key dimensions of the gear mount. Number 1 is the overall width of the part. Number 2 is the overall length. And number 3 is the bearing shaft diameter. Moving on to the critical dimensions, there are 2 that have been identified on the base. The first is the bearing shaft hole diameter, shown by dimension 5, with a tolerance of plus or minus 0.005 of an inch. This is to minimize the bearing shaft wobble and to ensure ease of turning during cranking. If the hole were too large, the shaft would be too loose and the pencil would not properly sharpen. If the hole were too small, then there would be too much friction and it would be very hard to turn. The second dimension is the sun gear pitch diameter, shown by dimension 4. That will have a tolerance of plus or minus 0.008 of an inch, and this is to ensure proper meshing of the gears during the cutting operation. The meshing of the gears is slightly less sensitive in tolerance due to the gear's ability to mesh with a wider range of fits. The last critical dimension is on the gear mount, identified as the bearing shaft diameter. That has a tolerance of plus or minus 0.005 of an inch, and that is to enable proper fit into the base, similarly as described with the bearing shaft hole diameter. Shown here is the process selection for the base of the pencil sharpener. The column on the left shows every process that is compatible with a non-ferrous metal. The shape is a 3D solid. The mass is approximately 0.5 kilogram. The section thickness is approximately 1.5 millimeters. The tolerance is plus or minus 0.005 of an inch. The surface roughness was not critical for this part, and the economic batch size was 100,000 units. There were 2 processes which passed all of these criteria, those being die casting and machining. We chose die casting to recommend for this part due to its automation and quick cycle time. Shown here is the process selection table for the gear mount. Similarly to the base of the pencil sharpener, the processes shown on the left are those for a non-ferrous metal, and the shape is a 3D solid. The only difference for criteria is the greater mass of 0.14 kilograms, which causes sand casting to fail sooner. Other than this minor difference, the 2 processes which pass the selection are the same, die casting and machining. We again recommend die casting due to its automation and quick cycle time.
The first component which was redesigned for manufacturing was the base. The holes on the base were combined to reduce the number of side poles. A lightweighting feature was added to reduce the material cost of the base, and the walls were made to have a more uniform thickness in order to bring down cost. After conducting analysis, the changes made in the previous slide reduced the cost per unit by 24 cents for a reduction of about 15%. The next part that was redesigned for manufacturing was the gear mount. First, uniform wall thickness was implemented. Next, we avoided sharp corners by filleting a few of the corner features, and we also reduced the thickness of the long arms that supported the front ring in order to bring down material costs. Finally, we avoided the internal depression, which was in the initial design. The changes made to the gear mount reduced the cost per part by 19 cents, which was a cost reduction of about 21%. Our design of product service system could be a 6-month helical gear replacement program, in which the company would ship a new set of sharpened helical gears to prolong the life and performance of the sharpener for the customer. So for a minimal annual charge, the blades can be replaced. Over the long run, this will improve customer satisfaction with the sharpener, as the blades will never become dull enough to have an impact on the ease of use of the product. From an environmental standpoint, this will reduce waste from consumers replacing entire units. Returned helical gears will be resharpened and sent back out to customers, thus reducing total waste.
In conclusion, we have identified areas for potential redesign of a mounted manual pencil sharpener based on analysis of function, cost, and potential modules. We tailored our product to the needs of individual consumers by creating a family of base designs that increase the modularity of the sharpener. The pros of our design are that it uses fewer parts while maintaining the same functionality, and that it can appeal to a wide range of customers. The cons are that the material changes and thickness reductions may make the device less sturdy, but we believe it will still function as intended. Potential further improvements include a more convenient way to remove the shavings catcher to minimize the amount of spilled shavings. If we were to start over, we could include more eco-friendly material choices and focus more on the environmental impacts of our product. Thank you for your time and attention.